Hello. In this lecture, we are going to discuss some theorems called the mean value theorems in differential calculus. And the first one we start with is called the theorem due to Rolle. It's called Rolle's theorem. And we will see the conditions and what is the assertion of the Rolle's theorem as we proceed. First of all, we are talking of a function f(x) defined in a closed interval a to b, and function f(x) is such that first condition is it is continuous in the closed interval a to b. Second condition is the same function is differentiable in the open interval a to b. That means it is differentiable in the entire interval excepting possibly at the endpoints a and b of the interval. The third condition is if f(a) is equal to f(b), that means that the endpoints of the interval, the value of the function f(a) and f(b), they are equal. Under these conditions, then the assertion is then there exists a value of x is equal to c inside the open interval such that the derivative f dash x vanishes at that point. That means f dash c is 0. I repeat once again, these are the three conditions: continuity in the closed interval, differentiability in the open interval. If it is differentiable in the closed interval, no harm, but the requirement is that the differentiability should be only for the open interval. And the third condition is f(a) is equal to f(b), then there is an assertion, there exists a value of x is equal to c such that f dash c is equal to 0, and this c is entirely within the open interval. Now here a couple of remarks have to be made. Number one is, when we say there exists a value of x is equal to c, this only implies that there is at least one value of c. In other words, it is possible to, we will go through some examples, it is possible to have cases in which the conditions are valid and between a and b there are two values of c such that f dash c is equal to 0, but the theorem says that there will be at least one c. So that is another way of writing, there exists at least one value of x is equal to c, and that c is entirely inside the open interval. The c does not coincide with a or with b. Now, number two, the remark is that this is a set of sufficient conditions. It is not a set of necessary conditions. That means there may be functions for which this condition holds even though all the above conditions are not valid. So the theorem has to be understood very carefully. It is a set of sufficient conditions. It is not a set of necessary conditions. This is sufficiency for this to be valid. So we will proceed further. We will take some few examples and see what happens. Historically, we may add that the third condition of f(a) equal to f(b), historically, originally, the third condition was like f(a) must be equal to f(b), and that must be equal to 0. Now, this has been removed. It is found that this is good enough. This is not necessary. We must remember that Rolle's theorem somehow originated from a study of theory of equations, where the main focus is to find roots of functions, mainly polynomial functions. And so at one point of time, when the theorem was originally stated, it was said that fa must be equal to fb is equal to 0. In other words, for fx, a and b were the roots of the equation fx is equal to 0. So one summary is that the conditions of Rolle's theorem are a set of sufficient conditions. This is very important. It is not a set of necessary conditions. It's very important because otherwise there are doubts in the students' minds as to really what's happening. Now we will take an example, and before that we will give the geometrical interpretation of the theorem by drawing a diagram. Now we get down to the geometrical significance of this theorem. We draw a small diagram and let's see what the geometrical significance of the theorem is. This is the x-axis and this is the y-axis, this is the origin. Now we have taken a function and called it y is equal to fx. We have drawn a horizontal line somewhere to cut the graph at 2 points, and we have taken this as x is equal to a and x is equal to b. So we see that this ordinate and this ordinate are equal. So here FA is equal to FB. Third condition is satisfied. Moreover, from the graph we can see that the function fx is continuous in the interval a to b. And if we look at the graph very carefully, everywhere we can draw a tangent. There are no kinks or sharp points. So we can draw a tangent everywhere. So the function is differentiable for all values of x between a and b. Now where exactly is the c? If we come here and draw a tangent, we see that the tangent is parallel to the x-axis. In other words, this is the value of c. So we assert that at x is equal to c, which lies squarely between a and b, f dash c, that means the tangent to the curve at the point c comma fc, is parallel to the x-axis. So the tangent to the graph of y is equal to fx is parallel to the x-axis at the point CFC. The x value is c and the y value is fc. So this is one example in which we have taken one value of c that lies between a and b. But as I said, that theorem says that there is at least one value. We will see a case in which there may be more than one value of C. So for that we need to rub out this diagram and create another one. So now we take up the case of example of more than one C. This is the y-axis. Here we have the origin. This is the x-axis. Let us take a horizontal line like this. Call this value of x as A and call this value of x as B. So our interval is from here to here. So evidently, again, we see that the function y is equal to fx has a graph that is continuous between a and b. There are no breaks. So this intuitively continuous. Fa is equal to fb. The ordinates at a and b are the same. This is the point x is equal to b, and this is the point x is equal to a. Again, since there are no sharp points on this curve, it is derivable. In other words, the tangent can be drawn at every point. So the function is differentiable everywhere in the interval a to b. No matter where we go, we can draw a tangent, and so on. Now we see that here in this case, evidently, this is one value of C. I mean the x value, this is, we can call it C1, and this is another value, we can call it C2. So here we see that the tangent here becomes parallel to the x-axis, and the tangent here also becomes parallel to the x-axis. So we have more than one C. And the Rolle's theorem is not flouted at all, because it asserts that there exists at least one C. When we say there exists a value of C, it implies there exists, this A means at least one. It's very important. So here is an example of two C's. Likewise, we can create more and more examples. We can get 3 C's or 4 C's. It's a matter of extension and nothing else. We will now take up one problem and see how the theorem can be verified.